Okay, now we'll talk about section 11.8 rotational work and power. As we know from before, the work is the force multiplied by the distance. Now, for rotational motion, if we have a body go under a force and rotating on the edge of this circle, okay? Let us zoom in this part. If the force acting from this point to this point, if we take it as an infinitesimal small part from the circle, then it is almost approximately as a straight line, not curved. This piece, we can name it delta x. Okay, then we have force acting on delta x distance, then we can find the work. What is delta x magnitude? In angular motion, we know that this section is equal to the radius multiplied by delta theta. We know that 2 pi r is equal to all of the circumference, right? But we need just a piece of it. A piece of it like this one. So we will not take 2 pi, the total angle, we just take delta theta. So delta x is equal to r delta theta, approximately. Okay, the force is equal to the work is equal to F multiplied by delta x. But delta x from here for rotational motion is equal to r multiplied by delta theta. We can combine r from here and if both of them, rf is tau. The magnitude of rf is tau. Theta between them is 90 degrees. Between the force, the central force, this force and r, the angle between them is 90 degrees. This is F, this is F, and this is R direction. The angle between them is 90, so sine theta is 1. So the work in rotational motion is equal to tau multiplied by delta theta. The force is tau. The displacement is angular displacement. Okay, change in position, in angular position. The power is work divided over delta t. Okay, the power in watts. We will not use just P because P is for the momentum. We use this power. Okay, the work is equal to, as we see here, tau delta theta over delta t. We can see that delta theta over delta t is omega, the angular velocity. As we find for linear motion, the power is equal to W over T or delta T, which is equal to F multiplied by the velocity. The velocity, the speed of the force is the power. Okay, now let us look at this example. We have this swing and this man pushing this woman, okay, a force during a time. This force remained acting on the woman for delta theta. He pushing from here to here. Okay, we have the length of the rope is L. Okay, the force of the man, the acting force is 100 newtons. The velocity, the angular velocity is 0.8 radians per second. The length of the rope is 3 meters. This delta theta is the delta theta when the force is acting on the moving body is 15 degrees. We need to convert it to radians by multiplying by 1. This is 1 by over 180. Then degrees will cancel. Then it will be 0.26 radians. Now find the work for this rotational motion and the power during this time or this theta, and find the time also at force effect time. Okay, the work is equal to tau multiplied by delta theta. Delta theta, we find it. The torque is R multiplied by F, multiplied also by sine theta. Look here, sine theta. But the force, this is the force, and this is R. This is the direction of R. That theta between them is 90 degrees. It is 1. The radius is 3. The force 100 Newton. So tau is equal to 300. Okay. Delta theta is 0.26 radians. Then the work is equal to, the work is energy. Its unit is joules. 78.5 joules. The power is the velocity of the force, or the angular velocity of the torque. The torque is R multiplied by the force, which is 300. 3 multiplied by 100. The angular velocity is given 0.8. Then the power is 240 watt. Okay, we can find the time. The power is equal to work over the time. So the time is equal to the work over the power. This will be equal to 0.33 seconds. It's almost 1/3 a second. This man pushes the woman, pushing the woman a third second, and the swing is going. This is a simple example. You can solve many examples like this. Thank you.